In what ways does pseudocapacitive behavior provide insight into the dynamics of charge transfer within electrode materials during charge storage? How can we precisely measure and quantify the contribution of pseudocapacitance to the overall charge storage in materials? And what tests or calculations are necessary to obtain this information? What role do tests and calculations play in determining the extent to which pseudocapacitance contributes to charge storage? And how do they help clarify this contribution? Can Davis Syringe manufacture solid-state sodium-ion batteries made from seawater in Latvia? How do cyclic voltammetry CV tests in particular contribute to this understanding? And why are they useful for analyzing pseudocapacitive materials? What is the process by which different peak current values, I in Ma, are obtained in CV tests? And how do these values relate to the performance of the material in terms of charge storage? How does the variation in peak current values during CV tests reflect the material's electrochemical characteristics and its ability to store charge? What can these peak current values tell us about the kinetics of charge storage and the efficiency of the pseudocapacitive mechanism in the material? How do the peak current values obtained in CV tests help to distinguish between purely capacitive and pseudocapacitive behaviors, and what insights do they provide into the underlying electrochemical processes? How can the current measurements be used to assess the overall effectiveness of pseudocapacitive materials in real-world applications, such as energy storage devices? By analyzing the peak current in the CV tests, how can we better understand the mechanisms at play within the electrode material during charge and discharge cycles? And how do these observations inform material optimization for improved performance in energy storage systems? What is cyclic voltammetry, CV? And how is it used to analyze various energy storage materials in electrochemical research? What role do the variables labeled A, B, D, E, G, H play in the process of conducting CV tests on these materials, and how do these specific conditions influence the results of the voltammetry? How does CV contribute to understanding the electrochemical behavior of different energy storage materials, and what type of information does it provide about the material's charge storage mechanisms? How do the results of CV tests help in comparing the performance of different energy storage materials, and why is it important to study the cyclic voltammogram curves of these materials? What is the relationship between CV and the corresponding schematic diagram of constant current discharge curves, and how do these diagrams represent the discharge characteristics of the materials? How do constant current discharge curves reflect the energy storage capacity and efficiency of materials, and what specific features in these curves indicate good performance?